Okay, so last time we looked at applications of the equilibrium constant, and we saw how you can use the equilibrium constant, the value, to be able to predict the direction of a reaction or calculate the equilibrium concentrations. So I want us to move forward, and this will be wrapping up this topic on chemical equilibria. Look at the factors affecting chemical equilibrium. So chemical equilibrium represents a balance between the forward and the reverse reactions. So you have the forward reaction and the reverse reaction taking place at the same time and at equal rates. So that means the concentrations of all the species in that reaction are constant when equilibrium is attained. So, but this particular balance that exists between the forward and the reverse reactions is a very delicate balance in most cases, meaning that if the experimental conditions are changed slightly, this may disturb the balance. And what happens is that it will lead to a shift in the equilibrium position. So one of the directions of the reaction will be favored, okay? So if you have a reaction of A and B giving you C and D, then maybe you want C and D to be the products that are produced. If you change the experimental conditions, it might favor either of the sides of that particular reaction. Okay, so there are variables, the variables that can be used that can be controlled experimentally are concentration of the species within a reaction, the pressure, and this is usually the case when you're dealing with gaseous species or gaseous reactants and products. The volume, this also applies for gaseous products or gaseous species in reaction, and the temperature. So these are the variables that can be controlled, and these would affect the chemical equilibrium. So we're going to look at each of these to see how any changes in these variables affects the chemical equilibrium. We'll also look at the effect of a catalyst on equilibrium. So when you introduce a catalyst, it tends to speed up a reaction. So what happens for the case where you have a chemical equilibrium exists? If you introduce a catalyst, what does it do? If it speeds up a particular reaction, how does it affect the equilibrium? There's a principle which is called the Le Chatelier's principle. This maybe you may have come across it in your chemistry career somewhere. It essentially helps us to predict the direction in which an equilibrium reaction will move when a change in any of the variables takes place. So changes in concentration, pressure, volume, or temperature. We can use this principle to predict which direction the equilibrium will move. So it simply states that if an external stress is applied to a system at equilibrium, the system adjusts in such a way that the stress is partially offset as the system reaches a new equilibrium. Okay, so the system there's a balance. If there's any external stress which affects any of these variables, then the system will adjust in such a way that to offset that particular stress. And then it will reestablish equilibrium. Okay, so let's first of all look at changes in concentration. And we look at examples of a reaction here. Iron thiocyanate, which is given by this formula, dissolve in water to give a red solution. Okay, so the red solution is because of the existence of these ions here. So the ones that have a red color. So this ion in itself dissociates. There's an equilibrium that exists for this particular ion because it dissociates to give us ion 3 ions and the thiocyanate ion, okay, which is colorless. The ion 3 ion is pale yellow. So any disturbance on this equilibrium for this particular ion can be observed by the changes in the color. Okay, so in itself it is red, but it dissociates to give us ion 3, which is pale yellow, and thiocyanate, which is colorless. So if either of the sides of this equilibrium is favored, you can observe by the change of color. If you see a pale yellow solution, then it means that this forward reaction is favored. If you see a red solution, it means that the reverse reaction is favored, formation of this particular ion. So we can consider for this particular solution, which has this equilibrium, we can consider various cases where you're adding particular ions. So adding sodium thiocyanate. So when you add, just a second. When you add sodium thiocyanate, essentially what is happening is that you're going to be adding the thiocyanate, ion into the solution. Okay. So when you add thiocyanate ion into the solution, it means that you are increasing the concentration of thiocyanate in this equilibrium up here. Just a second. So you're increasing the concentration of thiocyanate. So it means now the stress that you are introducing to the system is the increase in the concentration of the thiocyanate ion. So the system will move to restore the balance that it had at equilibrium. So for it to do that, it will move in the opposite direction to make sure that the extra thiocyanate ions that are introduced by adding sodium thiocyanate are used up in reacting with. So they will react with ion 3 ions to give us this ion. So because you're adding more of this, the system will move to use up the extra ions that are introduced. So the equilibrium shifts from left to right in that direction to ensure that the extra ions that are introduced are used up, so that it now reattains its equilibrium that it had. So how this is observed is that if the equilibrium shifts in that direction, then the red color will deepen, because you see the formation of this ion will be observed by the changes in the color of the solution. So more red color, so therefore the red color deepens. So that is how adding sodium thiocyanate affects the equilibrium. It shifts to the left. So it moves from left to right. Okay. Now, you can consider another case where you're adding iron 3 nitrate, okay, into the solution, into our equilibrium mixture that we had at the beginning. So what happens when you introduce this iron 3 nitrate is that you're introducing more iron 3 ions into solution. So you are increasing the concentration of iron 3 ions in the equilibrium mixture. So the system will move to correct that. And it does that by using up any extra iron 3 ions that are produced. So it will, for that to happen, the reverse reaction will be favored to use up any extra iron 3 ions being introduced into the system. So again, like the previous example, this is observed by the deepening of the red color of the solution. Okay. We can consider another case where you're adding oxalic acid. Okay. So oxalic acid has this oxalate ion. The oxalate ion, which is C2O4, and then I think it has a charge of -2. Just a second. This ion, which is the oxalate ion and has a charge of -2, is very, has a high affinity to iron 3 ions. So therefore, the oxalate ion, which maybe I can write here, the oxalate ion will bind any iron 3 ions that are present strongly. So that means it's as if it is removing the iron 3 ions from solution. So it is reducing the concentration of iron 3 ions from solution. So therefore, this kind of changes the equilibrium mixture in that the iron 3 ions reduce. So the system will move to replace the iron 3 ions which have been taken out of solution by the oxalate ion. So for that to happen, this forward reaction is the one that will be favored. So the equilibrium shifts from left to right, and the red solution turns yellow because now the forward reaction forms more of these iron 3 ions, and therefore this one is characterized by a yellow color. So therefore, also the formation of these ions, which are as a result of the oxalate binding with the iron 3 ions, is also yellow in color. So therefore, this will result in a yellow color being observed. Okay, so that is how concentration changes of the species affects the equilibrium that exists in a given system. We can also have changes in volume and the pressure. Changes in pressure do not affect the concentrations of reacting species in condensed phases. So if your reaction mixture is aqueous or you have solids, so therefore this one, any changes in pressure will not affect this equilibrium, because the condensed phases, that is liquid and solid, are virtually incompressible. So therefore, it does not affect the equilibrium that exists for such type of a reaction system. But if you're dealing with gaseous species or an equilibrium that involves gaseous species, changes in pressure will greatly affect the concentration of gases. Okay, because from the ideal gas law, we know that PV equals to nRT. So the pressure from this expression will be given by NV times RT, where this NV here is the concentration of the gas, N being the number of moles and V the volume of the gas. Because if you compress the gas, or if you increase the pressure of that reaction system, it means that you are reducing the volume. So therefore, this will affect the concentration. It will increase the concentration because you are reducing the denominator here in N over V. So if you do that, it will definitely affect the concentration of the gas, and this will also have an effect on the equilibrium constant. Okay. So for example, let's consider this reaction mixture here. This dissociation of N2O4 to give us NO2 and the reverse. We have an equilibrium that has been established at a particular temperature. So the question is, what happens if we increase the pressure of the gases by pushing down on the piston at constant temperature? So you have this, your reaction mixture here of these two species, and then you increase the gas by pushing down the piston. So what happens is that you reduce the volume of the gas or of the reaction mixture. So when you reduce the volume, what happens to the concentration? Remember, the concentration is the concentration of the gas is given by N over V. So if you reduce the denominator, it means that you increase the concentration of that particular gas. And if you consider the equilibrium constant expression for this, it's given by NO2 squared over the concentration of N2O4. Okay. So now if you increase the pressure, it means now you're moving the system from equilibrium. So therefore, you're not talking about the equilibrium constant anymore, but you're talking about the reaction quotient. So by reducing the volume, you have increased the concentration. Therefore, this particular numerator of this expression is going to be much larger because it is, notice that it is squared here. So when it becomes much larger, it means that QC becomes, it's a very large value compared to the KC. So therefore, QC becomes greater than KC. So therefore, the system will need to adjust such that QC will be equal to KC. It needs to return to equilibrium. And at equilibrium, QC would be equal to KC. So for it to do that, it means that it needs to reduce this concentration here of NO2 such that its square is becomes smaller and smaller until it is equal to Kc. Qc equals to Kc. So for that to happen, the reverse reaction is going to be favored. Okay, so we say that since the concentration of NO2 is squared in the equilibrium constant expression, the increase in pressure increases the numerator more than the denominator. Just a repetition of what I've said. So Qc will be greater than Kc, and the net reaction will shift to the left until Qc equals to Kc. Okay, let's consider a decrease in pressure now. So a decrease in pressure in this case would be the reverse of this particular diagram that we have shown here. Okay. So the reverse is the decrease in pressure. When you pull up the piston, you are reducing the pressure of the reaction mixture. So by decreasing the pressure, it means you're also increasing the volume. So therefore, N over V, you're increasing the volume. So that means you are reducing the concentration. Now, when you reduce the concentration of all the species, yeah, it has an effect on this reaction quotient here. It means now that this one, all these concentrations become small. So therefore, Qc becomes less than Kc. So for the system to now return to the equilibrium state, it means that there has to be a certain shift. It needs to increase this numerator for Qc now to become equal to Kc. So for that to happen, the forward reaction, which produces more number of moles, is the one now that is favored. So the forward reaction is favored. It moves in that direction until an extent where this numerator is large enough and Qc would be equal to Kc. Okay, so we say here that a decrease in pressure, which is also an increase in volume, would result in Qc being less than Kc. And the net reaction would shift to the right until Qc equals to Kc. Now, the same predictions that we have come up with here by considering the concentrations of the species can also be predicted using Le Chatelier's principle. So something has happened now, so the system will move now to correct that particular change or stress on the system. Okay. So for reactions in which there is no change in the number of moles of gases, a pressure volume change has no effect on the position of equilibrium. So notice here, in our reaction here, we had a change of the number of moles of the species. So you move from 1 mole to 2 moles. But if you have equal number of moles, meaning that there's no change of moles of gases from reactants to products, any changes in pressure or volume will not have an effect on the position of equilibrium. You can also consider another case where you have you can change the pressure of the reaction mixture without changing the volume. Now, how that can happen is that maybe you have a container that has a fixed volume, and maybe it has, in this case, you have NO2 and you have N2O4. So for you to increase the pressure in this reaction vessel without changing the amounts of these gases is by introduction of an inert gas. So for example, you want to introduce nitrogen into this system, or helium. Yeah, because these gases will not react with the species in the system, but they will increase the pressure of the system. Okay, so what happens is that what happens to the reacting gases, or the important gases that we are considering here, is that their mole ratio is what will change. Okay, only their mole ratio, or the mole fraction for that matter, is what will change, but their concentrations will be the same because the volume has not changed and the number of moles are also the same. Okay, so then therefore, any changes in pressure without changing the volume will also not have any effect on the equilibrium that exists. Another variable that we need to consider is the changes in temperature. Okay. Now, the other variables that we have considered, that is concentration, pressure, volume, they only alter the equilibrium position. That is the relative amounts of reactants and products, but it does not change the value of the equilibrium constant. The only variable that can change the value of the equilibrium constant is a change in temperature. Okay, this one will change the value of the equilibrium constant. We can illustrate this by still considering our example, the example that we looked at, that is the dissociation of N2O4 to NO2. Now, this reaction, there's a forward reaction and there's a reverse reaction. The forward reaction is usually endothermic in that it absorbs heat for N2O4 to dissociate. The reverse reaction is exothermic in that it results in the release of heat. So this is what you have. The forward reaction is endothermic. So N2O4 absorbs heat and forms NO2. So the enthalpy change is a positive value. Okay, so N, that is delta H, is positive. The reverse reaction is exothermic. So for NO2 to form N2O4, there's a release of heat, which means that the enthalpy change is negative. It's a negative value. So changes in temperature will affect these reactions, because we can consider that a rise in temperature adds heat to the system, and a drop in temperature removes heat from the system. So if you look at this reaction here, there's an equilibrium that has been established at a particular temperature. If you increase the temperature of this system, it means that you're adding heat. So the system will need to move to offset that increase in increase in heat. So therefore, it will favor the side of the reaction that uses the extra heat that has been introduced. So the side of the reaction that uses extra heat is the endothermic reaction. So the forward reaction is favored by increase in temperature. Now, if you reduce the temperature, meaning like now you are removing heat, the system will need to move to restore that heat that has been removed. So for it to do that, it will favor the side that produces heat, which is now the reverse reaction. So when you reduce the temperature, then the reverse reaction, which is exothermic, will be favored. Okay, so that's what you're saying here. The system shifts to reduce the effect of the change. A temperature increase favors the endothermic direction of the reaction, that is from left to right of the equilibrium equation. And a temperature decrease favors the exothermic direction of the reaction. Okay, that is from right to left of the equilibrium equation. So if you consider the increase in temperature, we are saying that the increase in temperature for this particular, let's just redo it here so that we can follow what are the point that I want to make. So if you increase the temperature, what happens? When you increase the temperature, the system will move to use up the extra heat that has been introduced. So therefore, it favors the forward reaction, which is endothermic. So this forward reaction means that now you have more NO2. So that means this particular numerator is going to be larger. So therefore, Kc becomes large. Okay, so therefore, you can see that when you increase the temperature, Kc will increase. Kc increases when the same system is heated. Now, when you consider the case when you reduce the temperature of the system, that is, you're cooling the system will favor the reverse reaction. Meaning now that the denominator here becomes large because this reverse reaction here is favored. So when the denominator becomes large, it means that Kc is going to become small. So that's why we're saying that Kc decreases when the system is cooled. Okay. Another variable that we said we are going to consider here is the catalyst. When you have a catalyst, introduce a catalyst to a system that is at equilibrium. A catalyst usually, I think this one is discussed in the reaction kinetics. A catalyst enhances the rate of a reaction by lowering the activation energy. Okay. So I want to consider, if you're considering, this is the energy diagram. You have here A plus B reacting to give us C plus D. There's usually an energy barrier that needs to be overcome for this particular reaction to take place. So this energy barrier is referred to as the activation energy. So what a catalyst does is that now it comes in to lower the activation energy such that the reaction path is like that, the one that I have dotted here. So now the activation energy is much smaller. So that's what a catalyst does. It enhances the rate of a reaction. It makes the reaction take place faster by lowering the activation energy. At normal conditions, this reaction will still occur, but it will take longer because there is this path that needs to be covered, which is longer. But when you have a catalyst, there is this path which is shorter, that is covered. But then this activation energy for a system where you have equilibrium now, it means that this activation energy is lowered for both the forward and the reverse reaction to the same extent. So this means the catalyst does not favor a particular side of that reaction. Both sides are enhanced in their rate. So then we can say, because of that, we can say that a catalyst does not alter the equilibrium constant in any way. The only thing is that it leads, because of the increase in the rate, so the forward reaction and the reverse reaction have an increased rate. It means that now the equilibrium is reached sooner than in the case where you don't have a catalyst. So equilibrium is reached sooner, but it does not affect the equilibrium. It does not alter the equilibrium constant. Equilibrium constant remains the same, and it does not favor either side of the particular equilibrium reaction. Okay, so this will be the end of our discussion on the equilibrium, chemical equilibrium. Our next discussion is chemical equilibrium, which we will discuss, I think the week of 9th to, is it 14th? When we are going to have a couple of classes. So that one we'll do a marathon of the brush through ionic equilibrium, because it's very important, dealing with acids and bases and defining what an acid is, what a base is, and how ionic equilibria determines whether you have a weak acid or a strong acid. Okay, so we look at those, and I think we'll be able to have covered most of the course content. So I want to stop there and wish you happy holidays, and see you next year.